Hello students, now we will discuss about the measuring instruments. As the name indicates, we are measuring some parameters or variables by using instruments. So, the definition of measuring instrument is measurements are the basic means of acquiring knowledge about the parameters and variables involved in the operation of the physical system. For example, when you are taking the calculation of area of a circle or area of square. So, when you are going to consider this area of circle, what is the parameter required in this? As the name this equation represented, A is equal to pi d square by 4. This is the standard equation we are using. The parameter to be measured is only d, because pi is constant in this, 4 is constant. The parameter to be measured is the diameter of the circle. Okay? To measure the diameter of the circle, we are going to use the scale. So, this scale will give the measurement in terms of centimeter or millimeter or meter. It is depending on how much length or wide it is. Okay. So, now when you are going to consider in terms of centimeter, suppose if d is equal to 4 centimeter, then what you are going to do? You are going to substitute that is 4 into 10 to the power minus 2 meter. If you are going to convert into meter, you are going to substitute it is 4 into 10 to the power minus 2 whole square divided by 4. So, like this you are going to consider it is pi into 4 square into 10 to the power minus 4, that is divided by 4. So, here you are going to consider pi d square by 4 in this manner. So, what you have measured in this area of the circle you have measured. So, by using scale, this is the instrument used to measure the area of the circle, means you are measuring some physical parameter or variable by using the instrument. Then measurement generally involves using an instrument as a physical means of determining a quantity or variable. So, here you used scale as a measuring instrument to measure the diameter of the circle to get the area of the circle. An instrument or a measuring instrument is therefore defined as a device for determining the value or magnitude of a quantity or variable. So, we are going to measure how much that quantity. So, we are going to measure that in terms of some units. So, all the measurement will have some units, that is suppose if when you are going to measure the quantity of water that is there in the bucket or some other this utensils, what you are going to do? You are going to represent the quantity of water in terms of liters. Okay. So, the liter is the unit for liquid material. So, like that, so for solid it is depending on the solid material, liquid material, or if you are going to measure that volume. So, volume, that is meter cube you are going to represent like that. So, the measuring quantity should be represented in terms of units. Okay. So, and also here you are going to consider the three parameters, that is the quantity you are going to measure, and then the unit, and then the device what exactly you are going to use. So, this is the basic of these measuring instruments. Since we are studying the electrical measuring instruments, what are the electrical quantities you think to measure? So, that is the first we will, whenever we are going to think about the electrical quantity, first we will think about the current and then voltage, power, energy, power factor. So, there are many parameters. So, we are going to measure. All you can measure, this current you can measure by using the instrument called a meter. The voltmeter is used to measure the voltage. To measure power you are using wattmeter. You are using this energy meter to measure the energy. Power factor meter, then phase angle meter. So, you are using for particular parameter, you are going to use that particular meter to measure the quantity. So, now since we are studying about the electrical measuring instruments, so we are going to consider the electrical measuring instrument, as its name implies, is based on the electrical principles for its measurement function. And also we are using the electrical measuring instruments to measure various quantities like electrical power, power factor, voltage, current, energy, phase angle, etc. Okay. So, now you see that what are the basic classification of these measuring instruments. The basic classification includes absolute instruments and secondary instruments. These absolute instruments are primary instruments. Suppose when you are going to measure something by using this primary instruments, it is not necessary to calibrate, means it is not necessary to compare that with some standard measuring value. So, whatever we are measuring, that will be itself we are going to consider it is a value, that is a desired value. When you are going to consider these secondary instruments, these instruments has to be calibrated at regular intervals of time, means you have to see that whether it is giving error or not. If it is giving error, you have to correct it. So, that process we are going to consider it is a calibration. So, how exactly you are going to do the calibration? The instruments, this is secondary instruments, whatever the reading you are getting, those readings you are going to compare with some standard instruments value. So, you are going to see whether it is generating some error or not, whether it is working properly or not. So, those instruments are called secondary instruments. These primary instruments do not require any calibration, but secondary instruments, so we have to calibrate at regular intervals of time. So, that is what the difference between the absolute and secondary instruments. Now, you see that what are these absolute instruments? These instruments give the value of electrical quantity in terms of absolute quantities, that is in terms of constants of the instruments and their deflections. Deflections later I will explain to you. So, whenever we are going to measure some electrical quantity, we are going to use one fixed part, another one is movable part. That fixed part is the spindle. For this, we are going to connect the pointer. So, here there will be a scale. So, this pointer will move from this initial 0 position to maximum. So, this is how we are going to consider those deflections. I will explain to you later in detail what is this deflection. So, in this absolute instruments, no calibration or comparison with other instrument is necessary, as I already told you, and they are generally not used in laboratories, and they are used or seldom used in practice by electricians and engineers. So, these absolute instruments are used by electricians and engineers. They are mostly used as means of standard measurements and are maintained by national laboratories and similar institutions. Some of the examples are tangent galvanometer, relay current balance, absolute electrometer. So, these are the some examples of absolute instruments. Now, we see what is secondary instruments. They are direct reading instruments. The quantity to be measured by these instruments can be determined from the deflection of the instruments. So, you have to see that how much deflection it is there from the initial 0 position to that what value, that angle you are going to measure, and then so you are going to consider the value in terms of that particular parameter. They are often calibrated by comparing them with either some absolute instruments or with some those which are already been calibrated with some standard instruments. The deflections obtained with secondary instruments will be meaningless until it is not calibrated. Always you have to compare with the standard values. These instruments are used in general for all laboratory purposes, like in our laboratory what we are using are the secondary instruments, the ammeter, wattmeter, voltmeter, whatever the meters we are using at our laboratories, all are secondary instruments. Some of the very widely used secondary instruments are, I already told, ammeters, voltmeters, wattmeter, energy meter. Energy meter is also called it as watt hour meter, because energy, as the definition of energy, we are going to consider it is the power consumed at particular time. The unit of power is watt, consumed at particular time. Since we are considering the time, we are representing in hour. Okay, it is a watt hour meter or ampere hour meter. So, we are considering this ampere hour meter is also a secondary instrument. So, now we are going to study in detail these secondary instruments, because we are not using that primary instruments at our laboratory. We are going to use only the secondary instruments at our laboratory. So, there are different parameters we are going to consider in the classification. The first thing what we have considered is classification based on the various effects of electric current or voltage upon which their operation depend. So, we know that whenever the current flows through some conductors, the heat will be generated, and also we are considering the magnetic effect. So, chemical effect, electrostatic, electromagnetic effect. Okay. So, that is why we have to consider that various effects of electric current, voltage. So, to classify these secondary instruments, ammeters, voltmeters, wattmeters, integrating meters depending on this magnetic effect. So, and also ammeters, voltmeters depend on the heating effect, the DC ampere hour meters depending on chemical effect. So, voltmeters are depending on electrostatic effect, and then AC ammeters, voltmeters, wattmeters, integrating materials mainly depending on this electromagnetic induction effect. Generally, the magnetic effect and the electromagnetic induction effect are utilized for the construction of the commercial instruments. Some of the instruments are also named based on the above effects, such as electrostatic voltmeter, induction instruments, etc. So, electrostatic voltmeter is mainly depending on this electrostatic effect. That is why we are going to call it as electrostatic voltmeter. So, then energy meter we are going to consider, it is a energy meter is the best example for this induction instrument. So, thus another parameter what we are considering for classification of secondary instrument is the nature of their operations. So, they are indicating instruments, recording instruments and integrating instruments. See that what are these indicating instruments? Indicating instruments indicate generally the quantity to be measured by means of a pointer which moves on a scale. So, example for this are ammeter, voltmeter, wattmeter, etc. These are the indicating instruments. So, recording instruments means, so this is the continuous process, okay. With respect to time we are going to measure, there will be paper and the paper, it may be a graph sheet, so or it may be, so some standard graph you are going to use that logarithmic or the normal scale. So, on that you are going to get that by using some pen or something. So, what it will do, the instrument is go on record that, like that what you are going to get, that ECG information, those are the recording instruments which are going to give that ECG signal, because it will continuously record on that graph sheet that what it is happening with the patient, okay. The best example is the ECG printout what you are getting from the instrument. Those type of instruments you are going to consider it as recording instruments. In our application also, in electrical applications also, sometimes we need that at some particular time the continuous variation of current, voltage, power, energy, etc. During that time we are going to use such type of instruments, those are called recording instruments. These instruments record continuously the variation of any electrical quantity with respect to time. In principle, these are indicating instruments, but so arranged that a permanent continuous record of the indication is made on a chart or dial. The recording is generally made by a pen or a graph paper which is rotated on a dice or drum at a uniform speed. So, the speed should be uniform in this case. The amount of the quantity at any time, means at any time means at that instant, may be read from the trace chart. Any variation in the quantity with time is recorded by these instruments. Any electrical quantity like current, voltage, power, etc. may be arranged to be recorded by a suitable recording mechanism. So, these type of instruments we are going to call it as recording instruments. The next type is integrating instruments. These instruments record the consumption of the total quantity of electricity, energy, etc. I already told you that the definition of energy, it is the power consumed at regular interval of time. Since it has come that interval of time, so what you are going to do is these instruments record the consumption of the total quantity, how much power is consumed in that particular time. So, that is called energy. So, these are called integrating instruments. The integrating instruments are going to give these such type of quantities during the particular period of time. That is, these instruments totalize the events over a specified period of time. No indication of the rate or variation or the amount at a particular instant are available from them. Means it is not going to give that at that instant of time, it is going to give over a period how much it is consumed. So, those type of instruments are called integrating instruments. Some widely used integrating instruments are, see, ampere hour meter, kilowatt hour meter means energy meter, kilovolt ampere hour, that is kVA RH meter. So, these are examples of integrating instruments. So, next will be the classification based on the current. We know that we have already discussed, that is what are the different types of currents you are going to consider, that is alternating current and also this direct current. I explained already that direct current machines. So, how exactly this alternating current generated is converted into this direct current. So, here to measure this alternating current, we require that alternating current instruments. So, and direct current quantities, we require the direct current instruments. This alternating current instruments are also called moving iron instruments. So, this direct current instruments, we are going to call it as moving coil instruments. So, and also some of the instruments can be used for the measurement of both the direct current and alternating current. So, depending on the kind of current, we are going to this classify the instruments into three categories: direct current instruments, alternating current instruments, and both the direct current and alternating current instruments. The next classification is based on the method used. Under this category, we have direct measuring instruments, then comparison instruments. Okay. So, direct measuring instruments, what it will do? This instrument converts the energy of the measured quantity directly into energy that actuates the instrument, and the value of the unknown quantity is measured or displayed or recorded directly. Directly you are going to measure in this. These instruments are most widely used in engineering practice because they are simple and inexpensive. Also, time involved in the measurement is shortest. Examples are ammeter, voltmeter, wattmeter, etc. By using this ammeter, directly you are going to measure the current. So, if it is DC, you are going to use moving coil ammeter. If it is AC, you are going to consider that moving iron ammeter. In case of voltmeter, you are going to measure the voltage directly. Wattmeter is going to measure the power directly. In case of this comparison instruments, these instruments measure the unknown quantity by comparison with the standard. You are going to measure the unknown value and then unknown parameter you are going to compare with the standard value. So, that is why it is called as comparison instruments. Examples are DC and AC bridges and potentiometers. They are used when the higher accuracy of measurement is desired. These you are going to use in high voltage applications, medium voltage applications, high current applications, like that, these comparison meters, because you can't consider that much voltage to be measured directly. That is why you are going to measure some value and then you are going to compare with some standard value. Okay. So, you are going to use that shearing bridge, then later you are going to study that is in detail in the measurement of electrical systems. Then the final classification is based on the accuracy. Whenever we are going to measure the value by using some instruments, it should not be, the tolerance limit should not be more than that plus or minus 5%. In some of the cases, it should be that plus or minus 2.2%. In some of the cases, it should be between, that is plus or minus 0.5%, then plus or minus 1%, plus or minus 1.5%, plus or minus 2.5%. The maximum value what you are going to consider is the tolerance limit, that is plus or minus 5%. This is based on the accuracy class of instruments. Next, these are the basic that classification you have seen. Next, you see that how exactly the instrument works. Mainly the torques you have to consider in this. I already told you that when I am explaining the DC machine, torque is a twisting moment. That is, due to the application of force, you are going to get this torque. Means it is when you are going to apply the force tangentially. I told you this. So, when the force is applied tangentially to this, there will be some twisting moment, means the rotation of this. So, what will happen? The torque is equal to, that is, it is depending on the force and radius of the circle. And also I explained the concept where this, the torque produced in DC machine. In DC machine, when you are going to consider that shunt motor, so what will happen here? The shunt field you are going to connect in parallel with the armature. Here there are two currents will be flowing. So, when the supply is given, what will happen? The current drawn by the motor you are going to consider it is I. The current flowing through the shunt field you are going to consider it is ISH. Then the current flowing through armature is IA. So, here what will happen? Since the current flowing through this shunt field winding, so the flux will be produced. That flux you are going to consider it as phi sh. And here one more current is flowing through the armature. Since the current flowing through the armature, what will happen here also the flux will be produced. Due to the interaction of these two flux, what will happen? There will be force exerted and there will be the twisting movement of the conductors of this armature. So, what will happen? There will be torque produced due to the force. This is force exerted on the conductor causes the torque. So, that is why the current flowing through, this is how the current flowing through the shunt field winding and the current flowing through the armature winding will cause the torque. So, now what will happen when there is when you are going to consider the instrument, we have that one is the fixed part, another one is movable part. So, movable part is a pointer. What will happen when we are going to consider the measurement, the deflecting torque will be produced. The deflecting torque will make the pointer to move from initial position to the maximum position. If we are not controlling this by using the controlling torque and also the damping torque, what will happen is, so this deflection whatever it is going to give, so we can't consider that whether it is correct or not. So, that is why we are going to consider this deflection torque has to overcome this controlling torque and also the damping torque. Now, you see that what is this deflecting torque, how exactly it is produced and how exactly this has to overcome this controlling torque and the damping torque. So, now the deflecting torque causes the moving system. Moving system, I told you that it is a pointer in case of wattmeter, ammeter and voltmeter. Moving system of the instrument to move from its 0 position. It may be produced by utilizing any of the effects. I already told you that it may be magnetic effect, it may be chemical effect, it may be electrostatic effect, it may be electromagnetic effect. It is depending on the meter. So, it may be produced by utilizing any of the effects of current or voltage in the instrument, such as, so I already mentioned these effects. The actual method of producing the deflecting torque depends upon the type of the instruments. The deflecting torque has to supply the following torque components present in an instrument. It has to overcome the deflecting torque required to overcome the torque due to inertia of the moving system. So, when this inertia will come, so we have seen this inertia component in the DC motor. So, we are going to consider this J is the moment of inertia, theta is the moment, that is in terms of rotation in radians. So, then the total torque due to this inertia, that is J d square theta by dt square, means the deflecting torque has to overcome this torque due to inertia, that is J d square theta by dt square. And also, so we will use that spring in the instrument. The torque has to require to overcome the controlling torque that is produced by the spring, the force of the spring, that is Tc is equal to Kc theta. So, this Kc represents the controlling torque constant and theta is the deflection. And then also this deflecting torque has to overcome the damping torque. So, Tv is equal to, that is Kv d theta by dt. So, where Kv is the damping torque constant. I will explain to you later in detail. So, how exactly these torques are going to produce. And also the torque required to overcome the frictional torque, that is called Coulomb torque. This component is minimized by appropriate design considerations. When we are designing itself, we can minimize this torque effect. So, now you see that how exactly this controlling torque is produced. So, to get that better operation, always the balance condition has to be upheld. Okay, that is controlling torque Tc should be equal to deflecting torque or operating torque Td. The controlling torque developed in an instrument has two functions. It limits the movement of the moving system. If it is not going to limit, so we will get that error in that reading. So, that is why it has to limit the movement of the moving system to give that better result by controlling torque, by considering the controlling torque, it should be equal to the deflecting or operating torque. And it ensures that the magnitude of the deflections always remains the same for a given value of the quantity to be measured, and it brings back the moving system to its 0 position where the quantity being measured is removed or made to 0. The controlling torque is dependent on the magnitude of the deflection produced. The moving system is deflected from 0 to such a position that the controlling torque at that deflected position is equal to the deflecting torque, means always it should be balanced. The controlling torque is entered in all commercial, we are going to consider in all commercial instruments by any one of the following three ways. One is by means of one or two coiled springs. The corresponding instrument is termed as spring controlled instrument, and then by the action of gravity due to suitably placed weights on the moving system. Such instruments are called gravity controlled instruments, or by using permanent magnet. These instruments are called magnetic control systems. Spring control is now always universally used. The gravity control is employed in few cases, and special laboratory types and magnetic control is applied of some galvanometers and certain moving iron instruments. So, now you see that how exactly we are going to consider the construction of this spring control. Here you have that two pivots, that is a spindle is placed between the two pivots, and you have mounted this, see here there are two springs A and B in the opposite direction. So, one end of this spring is fixed to this spindle, and one more this part is there, this is the movable part. This spindle is the fixed part and this is the movable part. This is how we have that spring in strip form. So, how it works, you see that now you have one spindle, you have two springs and one is the pointer. So, now the moving system, this I already told you that this spindle is fixed between the two pivots. The moving system is attached to the spindle. Two phosphor bronze hair springs A and B wound in opposite directions are also shown, and the inner ends are attached to the spindle. The outer end of spring A is connected to the lever, which is pivoted the adjustment of which gives 0 settings. The outer end of B is fixed. When the pointer is deflected, one spring unwinds itself while the other is twisted. Any one of the spring unwinds itself and the other one is twisted. This twist in the spring produces restoring or controlling torque, which is proportional to the angle of the deflection of the moving system. Suppose if you are considering E be the Young modulus for the material of the spring and theta be the deflection of the moving system to which one end of the spring is attached, then the controlling torque developed in the spiral spring, you are going to represent it as Tc is equal to Eb t square divided by 12 L theta. That is, since only theta is variable in this, the other quantities are fixed, we can consider this Tc is equal to Ks theta, where L is the length of the spring strip, B is the depth of the strip, like we have considered it is a depth, and this is the length and this is the thickness of the strip. T is the thickness, Ks is the spring constant. The controlling spring must meet the following requirements. The stress developed in the spring must be well below the elastic limit of the spring material at the maximum deflection of the moving system. So, the maximum stress is represented by using this S max. So, this is essential to avoid fatigue and to preserve the stability over a long period. That is why we must have this L by R ratio is equal to E theta divided by 2 S max, where S max is the maximum stress which must not exceed, and for full scale deflection theta should be 90 degree. The ratio L by T you are going to consider it as about 3000 in a good instrument. If springs are used as leads of current to the instrument, their cross sectional area must be sufficient to carry the current without overheading them, failing which the consistency will be impaired. The spring material should also have the following properties. You see that what are the following the spring material should have? It should have low resistance. The temperature coefficient should also be low. The spring must be of non-magnetic material. In a permanent magnet moving coil type instrument, the deflecting torque is proportional to the current passing through them. That is why this Td is directly proportional to I. Then for spring control instrument, the controlling torque T is directly proportional to theta, that is the deflection. So, under this condition, when you are going to consider that balance condition, TD is equal to TC, see this Ki is equal to that Ks theta, means current is directly proportional to deflection. The pointer comes to rest when the deflecting torque and the controlling torque or restoring torque are both are equal. TD is equal and opposite to TC. So, this is what we are considering. Under that condition, I is equal to Ks theta divided by K. This is the equation. This gives the relationship current is directly proportional to the deflection. So, next this is about the spring control. Now, you see that how exactly we are providing controlling torque by using this gravity control. In this case, we are going to use this small weight, that is control weight, we are going to put on the spindle. Here also there is one more weight to adjust that 0. This is going to balance, and we have this movable part. Okay. So, here when the controlling torque 0, that what will happen here, when the control weight is vertical, so the controlling torque is 0, and hence the pointer reads 0 at this point. So, when the deflection torque lift the controlling weight from position A to B, so what will happen here, it is going, you are going to get the angle theta. This is when the moving system is rotated, you are going to get the deflection. So, this is then due to gravity, a restoring torque is exerted on the moving system. In this case also you have to consider that when TD is equal to theta TC, so then only you are going to get the proper value. Here you see the equations, the controlling torque TC is given by, that is WL sin theta, that is we are going to consider it is kg sin theta. Kg is the constant for this gravity control, where W is the control weight, L is the distance of the control weight from the axis of the rotation of the moving system, kg is the gravity constant. And we know that TD is directly proportional to I, that is why we are representing is TD is equal to Ki. When we are considering that equilibrium condition, the TD is exactly equal and opposite to TC, what will happen? There will be an equilibrium condition, that is called balance condition. When TD is equal to TC, so we have the value of this Ki, and the TC is, we have the value of this TD is equal to K into I, we have the value of this TC is equal to Kg into sin theta. Under equilibrium condition, when we are equating this, the current I is equal to Kg divided by K. So, now you observe this I is directly proportional to sine of the angle, or that is the angle is the deflection angle. Current I is proportional to sin theta, not it is theta in case of this gravity control. But in case of spring control, I is directly proportional to theta. In case of gravity control, I is directly proportional to sin theta. Hence, in gravity controlled instrument, the scale is not uniform because it is sinusoidally varying. The deflection is sinusoidally varying. That is why in case of gravity controlled instrument, the scale is not uniform. It is cramped for the lower readings instead of being uniformly divided. For the deflecting torque assumed to be directly proportional to the quantity being measured in this case. Next, we see the advantages of gravity control. It is cheap and not affected by temperature variations. It does not deteriorate with the time. It is not subject to fatigue. What are the disadvantages? Since the controlling torque is proportional to the sine of the angle of deflection, the scale is not uniformly divided but cramped at its lower end. It is not suitable for use in portable instruments in which the spring control is always preferred. Gravity control instruments must be used in vertical position so that the control weight may operate and also must be levelled, otherwise they will give 0 error. So, these are the disadvantages of gravity control. So, in all practical applications what we are using in our labs, we are going to use that spring control. So, now you see that the damping torque. Damping means, so here you are going to get that there are 3 conditions mainly. So, we are going to consider the damping ratio to judge whether it is under damped, over damped and critically damped. Usually we will consider the symbol zeta for this. Zeta, when zeta is equal to 1, we are going to consider it is critically damped. When zeta is less than 1, we are going to consider it is under damped. when zeta is greater than 1, we are going to consider it is over damped. So, damping means we are going to get that oscillations. So, here as it is indicated in this graph, you see that in case of under damped, we have this more number of oscillations with the maximum overshoot. In case of over damped, you see that, so here the overshoots and undershoots are reduced. In case of critically damped also, it is reached to the required value at the minimum time. Okay. So, compared to this over damped. So, it is depending on the damping ratio. To overcome this difficulty, this difficulty of the deflecting torque, what we are getting, so that is the action of the deflecting torque. So, on account of this control torque, so we are not getting exactly that Tc is equal to Tb, Td, that is the deflecting torque. So, both are, we know that both should be equal and opposite to each other. Due to some inertia of the moving system, the pointer will not come to rest even though the Tc is equal to Td. So, immediately, but some oscillations will be occurred in that. To overcome this, we are going to consider this damping torque is to be developed by using the damping device attached to the moving system. The damping torque is always directly proportional to, that is, rate of change of deflection. Okay. So, that is the speed of rotation. So, you are going to consider this d theta by dt is the speed of rotation of the moving system. So, kV is the damping torque constant, d theta by dt is the speed of rotation of the moving system. I already told you that there are 3 different conditions of damping. Under damped condition, in this the response is oscillatory. Over damped condition, the response is sluggish and it rises very slowly from its 0 position to final position. Under critically damped condition, when the response settles quickly without any oscillations, the system is said to be critically damped. So, how exactly the damping torques are produced? Here we have 2 methods: air friction damping. There are 3 methods: air friction damping, fluid friction damping and eddy current damping. See here, in case of this air friction damping, we have the vane fixed to this spindle and then there is a pointer. Okay. We can arrange in this manner or you can arrange in this manner. So, when you are going to consider the damping, you are going to consider with the light vane or vanes having considerable area is attached to the moving system to develop a frictional force opposing the motion by reason of the air they displace. There are 2 ways of connecting in this. So, in the first way of connecting, you are considering that light aluminum wave, here the light aluminum vane, here also you are considering that light aluminum spindle with this. So, you are using aluminum as a material for that light aluminum vane, which moves in a quadrant shaped air chamber. The chamber also carries a cover plate at the top. The vane is mounted on the spindle of the moving system. The aluminum vane should not touch the air chamber walls, otherwise a serious error in the deflection of the instrument will be introduced. You have to take care of this. Now, with the motion, the vane displaces air and thereby the damping force is created on the vane that produces the damping torque on the spindle. When the movement is quicker, the damping force is greater. When the spindle is at rest, the damping force is 0. This is the principle of working we are considering in this. And then when you are considering this second setup, so how exactly it works? It consists of light aluminum piston which is attached to the moving system. The piston moves in a fixed chamber which is closed at one end. Either circular or rectangular chamber may be used like this. So, this is the rectangular or circular chamber what you can use. The clearance between the piston and the chamber walls should be uniform throughout and as small as possible. When the piston moves rapidly into the chamber, the air in the closed space is compressed and the pressure of air thus developed opposes the motion of the piston and thereby the whole moving system. So, thereby you are going to consider the movement of the moving system. If the piston is moving out of the chamber, so rapidly the pressure in the closed space falls and the pressure on the open side of the piston is greater that on the opposite side. This motion is thus again opposed. With this damping system, care must be taken to ensure that the arm carrying the piston should not touch the sides of the chamber during its movement, otherwise you will get the error. The friction which otherwise would occur may introduce a serious error in the deflection. The air friction damping is very simple and cheap, but care must be taken to ensure that the piston is not bent or twisted. This method is used in moving iron and hot wire instruments. This is how we are going to generate the damping torque by using air friction damping. Next, you consider this fluid friction damping. As the name indicates, you are considering the fluid, okay, it may be oil. So, here the disc you are going to move in this, so it will rotate and there is a fixed part that is called a spindle. So, you can consider this arrangement also. The vane, this is also this, the spindle is circle here, okay. You can have the vane to fitted to this spindle. So, here it is rotating in this way, okay. So, how exactly this works, you see that this form is damping similar to air friction damping. The action is the same as in the air friction damping. Mineral oil is used in place of air, and as the viscosity of oil is greater, the damping force is also much greater. The vane attached to the spindle is arranged to move in the damping oil. So, it is rarely used in commercial type of instruments. The oil used must fulfill the following requirements, that is, it should not evaporate quickly. The oil should not evaporate quickly. It should not have any corrosive effect on the metals. Its viscosity should not change appreciably with the temperature, and also it should be a good insulator. So, here the disc is attached. Due to the rotation of the disc, we are going to consider the fluid friction damping. The advantages are, the oil used for damping can also be used for insulation purpose in some forms of instruments which are submerged in oil. You can use this oil for the purpose of producing the damping torque, and also it can be used as a insulation. The clearance between the vanes and the oil chamber is not as critical as with the air friction clamping system. This method is suitable for use with instruments such as electrostatic type, where the movement is suspended rather than pivoted. So, due to the upthrust of oil, the loads on bearings or suspension system is reduced, thereby reducing the frictional error. So, this is about the advantages of fluid friction damping. So, now you see that what are the disadvantages. The instrument with this type of damping must be kept always in a vertical position. So, you can't change the position, always you have to keep it in vertical position. It is difficult to keep the instrument clean due to leakage of oil. It is not suitable for portable instruments. The fluid friction damping can be used for laboratory type electrostatic instruments. So, and also you can develop this damping torque by using that eddy current. Eddy current, we know that. So, actually when this is due to that damping magnet. So, here north pole and south pole, in between the north pole and south pole, what will happen when the current flow, there will be a magnetic field produced. When the conductor rotates in the magnetic field, what will happen, the EMF will be induced and also the eddy currents will be produced. Okay. So, this is how we are going to consider in this. So, like this, the conductor is rotating in the magnetic field. So, here north and south pole, here the magnetic field will be produced. Here you are going to consider that damping disc, it is attached to the fixed spindle and the pointer is attached to this. So, eddy current damping is the most efficient form of damping. The essential components in this type of damping are the permanent magnet and a light conducting disc, usually of a aluminum. When the sheet of conducting material moves in a magnetic field so as to cut through the lines of force, the eddy currents are set up in it and force exists between these currents and the magnetic field, which is always in the direction opposing the motion according to Lenz's law of magnetic field. This force is proportional to the magnitude of the current and to the strength of field. The former is proportional to the velocity of the movement of the conductor. and thus the magnetic field is constant. The damping force is proportional to the velocity of the moving system and is 0 when there is no movement of the system. Since it is depending on the velocity, so when the moving system is not moving, what will happen? It will be 0. So, there I already explained these two ways of connecting. Okay. So, now you see that, and also the electromagnetic, how exactly we are going to get this in the electromagnetic effect also we will have the two magnets. So, how exactly we are going to get the movement of the coil in a magnetic field produces a current in the coil which interacts with the magnetic field to produce a torque, that I already explained in DC machine principle. This torque opposes the movements of the coil and slows the response. The magnitude of the current and hence the damping torque is dependent upon the resistance of the circuit which the instrument is connected. The damping method is used in galvanometers. These type of damping methods we are using in galvanometer. Means the deflecting torque has to overcome the controlling torque and also the damping torque. So, now you see that what are the different types of this deflection instruments. In these type of instruments, pointer of the electrical measuring instrument deflects to measure the quantity. The value of the quantity can be measured by measuring the net deflection of the pointer from its initial position. So, in order to understand this, you see this diagram. Okay. Here in between the two permanent magnets, see here the spindle, you have the spindle, the spring is connected to that and the movable part, the pointer is attached to this. So, this spring is used to generate the controlling torque. So, to avoid error in the deflection. Okay. So, now what will happen here when the magnetic field in the air, when the conductor rotates in the magnetic field, what will happen here? Due to that the pointer will move from the 0 position to the maximum. Here suppose if you are considering this is 0, so it will start from 0 to the maximum. Okay. And then what will happen? So, when it there is no connection, what will happen when the parameter to be measured you have already measured. So, you can bring back this due to the this torque, that controlling torque produced due to this spring. It has two permanent magnets which is called the stationary part of the instrument and the moving part which is between the two permanent magnet, that is this pointer. Okay. That consists of pointer. The deflection of the moving coil is directly proportional to the current, that is why this Td is directly proportional to this current. So, Td is equal to K into I. This K represents the proportionality constant which depends on the strength of the magnetic field and the number of turns in the coil. The pointer deflects between the two opposite forces produced by the spring and the magnet, and the resulting direction of the pointer is in the direction of the resultant force. The value of the current is measured by the deflection angle theta and the value of K. So, now you see that what is the difference between this deflection instrument and the null instrument. So, null type instrument, so in opposite to this deflection type of instrument, the null or 0 type electrical measuring instrument tend to maintain the position of the pointer stationary. So, here it is going to maintain the position of the pointer stationary. They maintain the position of the pointer stationary by producing opposing effect. So, how exactly we are going to produce this opposing effect, you see that. Thus, for the operation of null type instruments, following steps are required. This value of opposite effect should be known in order to calculate the value of unknown quantity, and detector shows accurately the balance and the unbalanced condition accurately. The detector should also have the means for restoring force. So, this is about the null type instruments. So, now you see that what are the advantages and disadvantages of deflection and null type measuring instruments. Deflection type of instruments is less accurate than the null type of instruments. It is because in the null deflecting instruments, the opposing effect is calibrated with the high degree of accuracy, while the calibration of the deflection type instruments depends on the value of instrument constant, hence usually not having high degree of accuracy. Then null type instruments are more sensitive than the deflection type instruments. Deflection type instruments are more suitable under dynamic conditions than null type of instruments. as the intrinsic responses of the null type instruments are slower than deflection type of instruments. So, we are using mainly the deflection type of instruments at our laboratory. Okay. So, what are the important functions of the electrical measuring instruments? So, here we have indicating function, recording function and controlling function. What is this indicating function? These instruments provide information regarding the variable quantity under measurement, and most of the times this information are provided by the deflection of the pointer. This kind of function is known as indicating function of the instruments. So, we are going to get the value by the deflection of the pointer. In recording function, these instruments usually, I already told you that we are going to use paper and pen to record the values. So, that is why these are called recording instruments. In controlling function, this function is widely used in industrial world. In this the instruments controls the processes. Okay. When you are going to consider the characteristics of electrical instruments, we have static characteristics and dynamic characteristics. In static characteristics, mainly we are considering the accuracy, sensitivity and reproducibility. So, accuracy, it is desirable quality in measurement. It is defined as the degree of the closeness with which instrument reading approaches the true value of the quantity being measured. Accuracy can be expressed in three ways, that is point accuracy, accuracy as the percentage of the scale of the range and accuracy as percentage of true value. When you are going to consider the sensitivity, so it is also a desirable quality in the measurement. It is defined as the ratio of the magnitude response of the output signal to the magnitude response of the input signal. So, now you see that what is reproducibility. So, it is defined as the degree of the closeness with which a given quantity may be repeatedly measured. High value of reproducibility means low value of the drift. Drift are three types: zero drift, span drift and zonal drift. Now, you see that what is a dynamic characteristic? These characteristics are related with the rapidly changing quantities. Therefore, in order to understand these types of characteristics, so we are required to study the dynamic relationship between input and output. What are the relationship between the input and output? How exactly the output changes with respect to input? So, I am going to stop at this stage. So, these are the basics what you have considered for the measuring instruments and the characteristics, the different types, and then what are the torques we are going to consider. So, next in the next class I am going to explain to you this dynamometer type wattmeter and also the induction type energy meter. Okay. So, thank you very much.